Okay, I'd like to welcome everybody to the first session, which is referred to as paper session 5. And the first paper of the session is by Eric Dullin and David Jamet, who will be a joint presentation. The title is Scientific Evidence of Telekinetic Effects on a Spinning Mobile, the scientific attempt to detect and study telekinetic effects even in a non-confined environment.
So that's it. Thank you.
Take it away.
Okay, good morning. I would like to thank first the Parapsychological Association for inviting us to present our work. I'm sorry. Thank you. Thank you. And I am Eric Dullin. I'm conducting research in the LAPDC lab in France, a private lab funded by David in 2012 with a collective of researchers. And since then we conduct different research, mainly on telekinesis. I would like to thank all the people who have contributed to this project in one way or the other. So our topic is to present a scientific attempt to detect and quantify the telekinetic actions on a spinning mobile. So first, I would like to say that we are speaking about telekinesis versus psychokinesis. It's just to be more neutral about explanation because there is no psycho in it. Okay? So let's dive directly on our topic through two quick videos. So the first one. This is a normal speed. So, is this telekinesis, or is it just an aerodynamic thermic effect induced by the hand's heat? That's all the questions, and many people have worked on this since 18th and 19th century. I have to go very quick here, but you can look also to the work of Carlos Alvarado with his paper on human radiation in 2006, which detail very many information about all the past mesmerism period, spiritism, and so forth. But very quickly here, so on the here, oh, sorry. So here we have the biometer of Baraduk, which was mainly a needle suspended to a thread. And so when you approach the hand, the needle was making some deviation, and they were measuring the deviation. Then in the same approach, there was a stenometer from Poltra. And after, there is the Tromlens motor, which are mainly a cylinder of paper with a straw in it. And the straw is, there is a needle through the straw, vertical, and put on a coin, and you can so turn the cylinder of paper. Sorry. And 60 years after, we can find some very close motors, which was psychotronic motors from Julius Kremski, a Czech engineer. In fact of that, there is many critique or explanation of this movement. Many people say that it's only physical. So we go very quickly on that. So in earlier time, in 18th, there is already a paper of Netiev who make a point to saying that the movement of the mobile with approximated hand was due to the heat of the hand, so the current ascendant on the hand, which was different at the center of the hand at the end. We can talk also about Varcollier, who puts the hypothesis that the current stream by the body, ascendant stream of the body, pull the air on the table. We are looking at this one. And so the air on the table, if you put an obstacle like a hand in front of it, you put a dissymmetry in the flow, and so there is a torque on the mobile, and so the mobile runs. And the last, I would say, there is many other people who work on that, but I could just mention also John Rodkin, which is an engineer of the SPA Association in England. We wrote an article in SPA and about the Egli wheel. The wheel, it's something like that, you know, it's a commercial product, which is normally, its objective is to measure the vital force of the hand. And so John Rodkin made a paper and said that on his experience, he don't see any movement of the product which was not induced by thermic or aerodynamic effect. So, how these things could be approached? We think that mainly in the telekinesis space, there is a two-way of approach. The first way is to try to complete isolation the target system. So for example, here we have one container, glass container, above different mobile, sea wheel, I would say. Here it's a double container superimposed. And here it's one container and inside a Faraday grid, in order to avoid electromagnetic influence. So this is a way to work. The problem and the drawback of this approach is the possible phenomenon in vision, as mentioned often by Robert Jan and Brenda Dune of the Pierre Institute. You have to very often to leave some uncertainty and less constraints to the system in order to have a greater phenomenon. And that's that's one point. The other point is was very well presented by other presenter and Roger yesterday or 2 days ago about the microteca approach, which is more a statistical approach with very small event. And so we are trying to be between these two approaches. I would say. So first we make a partial isolation of the systems. So we try to lower the physical perturbation. And then in parallel, we put some measurement system to control the other remaining factors. So to be able to work in a non-confined environment, but control what's happening. And so in this case, we are not in a statistical approach. We are more on a physical approach. We say we have to have a good signal to noise ratio, which could be easily expressed by looking to all the other physical perturbation. If I have a normal perturbation which is bigger than the other physical perturbation, plus the margin of error in the measurement, I have kind of effect. So we use a mobile to work in LAPDC. So mainly it's I bring one here. So it's a cup of plastic. It's hemispheric dome, plastic dome. So it's no magnetic. And we put that on a needle with a cork plug, preferably French wine. But you can use Greek wine. Wine is very nice too. Or you can use also a cup of plastics and with the needle. So anybody can do that, and we bring some, so you can bring to home and try if you want after. Okay. So the weight of the mobile is 2.5 grams. So it's mostly heavier than this one, which is only half a gram. So why we make this choose? Because we want to have a mobile not too much sensitive to airflow, okay, and also because of the hemispheric shape and the smooth surface, the air is there is no many things to take for the air to grip on, so it's smooth. So and the way to make the experiment is there is a telekinesis experimentator. So I use the term techist. It's easier. So telekinesis experimentators. Just a point on this. In LAPDC, we foster a team of people who discover telekinesis, who practices and try to develop their abilities, sometimes only for games. And I make some connection with Michael. Michael talked yesterday because some of this kind of people are online. So we take contact to them through online chat, and then we give them some mobile so they can test, and we can test if they are credible and if they can work with us in our work. So, I'm sorry. So yes, so in this kind of experiment, so I list the different potential forces that we have. So we have the vibration, because the hand is just close to the mobile, so you can imagine that there is some kind of vibration. So we make some tests with loudspeaker and accelerometers. You can see on this slide. To see if I use a good vibration, I can make several turns of the mobile. Because our objective is that the mobile is running several turns. So it's not just a small movement we are looking for. We are looking really to the mobile turning several turns. So with I will have to go quicker. So for the vibration, it's here, and for the statics we use a generator just close to the mobile, and try to turn it with static effect. And so we have only half turn in a way and half turn in the other way, so swinging between two positions, which is normal because if you want to turn the mobile, you have to take the generator and turn around like this. And so on internet there is some video, people show that they can put their hand and they follow the mobile follows the hand, so this could be really a static effect. But if the hand is not moving, you have difficulty to have more than a half turn effect. So once we have looked to the mechanical, magnetic, we talked about it before. Electrostatics, radiation, it's mainly a heat effect because the pressure radiation is marginal. So we have the last effect, which is aerodynamic. So it's why we focus on this effect because we think that it's more difficult to apprehend, and also because we are looking at very slow speed airflow between 1 millimeter per second to 20 centimeters per second. So we can't use anemometers or something like that to measure. We have to find other methods. So it's why David works with University of Poitiers and the PIM laboratory to elaborate a method to measure this airflow and visualize and measure the speed of the airflow around the mobile. So this method is called PIV, which is the contraction of particle image velocimetry, and I will go very quickly on that. First, we use a semi-confined cabin, which is clearly like a phone booth with a curtain. Inside you have a table with the target. Here we have a smoke generator. We generate smoke inside the cabin. The techist is here, and he will try to move the target with his hand. We have a laser, and the laser is eliminating the smoke particle, so to have a thin slice, or horizontal slice of particle eliminated. And on the vertical side, we have the camera, which is looking to the image. So you will see directly this on this slide. So here we have the smoke generation. Here you have the thin slice crossing the mobile, so of smoke. You can see the mobile and the hand, and here you have the what is seeing the camera. Fine. So we have processing softwares which work on calculating the speed of the airflow by looking at the gap between two sequential images. So, for example, on this we have two images separated by 40 milliseconds. Okay, and if you look to the front cloud point here, it moves from here to here. So the gap is x millimeter. And so the software is able to calculate the speed using the displacement and the elapsed time. And so the software it identify all patterns you could find on the image, on the first image, and trying to find the same pattern on the second image, and look how was the displacement and so the speed. So here we have a vector field representation. Each arrow are in fact the speed on the considered point. And some are, for example, these are green arrow, but some are orange. It's because if the system has not sufficient information to calculate, it makes some interpolation between close other arrows. So this was between two sequential images. So for example, separated by 20 milliseconds. And here we have the result for a total elapsed time of the experience. So we see the global flow of the air around the mobile. I'll sometimes the time to go through the next one. I will do that here. So the first thing, so now we have the speed around the mobile at different time. But what we are interested in is to see the evolution of the speed of the mobile compared to the evolution of the airflow around the mobile. So we take the speed on a different concentric cycle. We take 100 points on each cycle, separated by 1 or 2 millimeters, and on each point we have the tangential speed. Okay? And then, so I will go very quickly on that. We have our cycle, so we have 100 points per cycle, and we have here the evolution speed of the mobile using another software. And so we consolidate all this data in one numerical model, which could be around 9 million points for 1 minute experience. And from this, we are able to make some scan to have different representation and different granularity as in space or in time. For our presentation, we are focused on one kind of presentation, which is the mean evolution of the airflow compared to the mean evolution of the mobile. And when I say mean evolution of the airflow, close to the mobile, so at 1 or 2 millimeters from the mobile. So we conduct 8 experiments on this presentation. The first experiment, so 3 kinds of experiments. The first experiment, we try to generate the motion of the mobile with airflow. So we use some pump machine and smoke generator, and I will try to show you how it works. It's always better. So here we have the pipe. So the air is moving tangentially, and our mobile is running. So this is kind of reference experience, okay? So then we use this time a motor. So in fact it's an electric motor moving a needle which is flattened and stick on the mobile. So we run the mobile. So you see how the flows are moving when you run the motor. And on the end we make a quick acceleration to see the impact of the airflow around the mobile. Okay.
Is that the original speed?
Original?
Is this the original speed?
Yeah. It's not accelerated or decreased. And so and the third one is with techist, so telekinesis trained people. So you see the hand is here, you have the airflow around, and you see the mobile. So that's the 3 kinds of experience we did. And the way to compare this experiment, so there is 3 categories, and the way to compare is to take the ratio between the mobile speed and the mobile periphery airflow speed. Okay? So I will just extract 2 or 3 because we don't have time to go all through. So this is an experiment, as we see on the first category with airflow. I have to go faster. So very quickly, here is a calculated speed around the mobile. Okay, you see that directly. You see the airflow and the detachment here. And here is you have on this diagram the mobile speed, which moves from 0 to 39 degrees per second in red. And here you have the airflow speed compared. So you see that your airflow speed has to be between 50 to 120, so average 25, in order to start the mobile. Okay. On the next slide, we compare this to the techist approach, where there is a telekinesis people around the mobile. And so the mobile speed is here in red, okay? And here in orange is the airflow speed at 2 millimeters from the mobile. So you see that the speed is moving up above the airflow compared to here where the airflow has to be twice as high as the mobile. And now we are looking at an experiment where the mobile is already launched. So it's a global 6-minute experiment. So the global mobile speed was here. And we make an extraction on this global experiment of 1 minute to see the airflow speed. And here you see the airflow speed is 40 degrees per second compared to around 6-7 degrees per second for the airflow. So it's pretty obvious difference. So to sum up the result of the experiment, we have our 3 categories, remember? So the airflow experiment is here, the motor, drive by motor and drive by telekinesis. And so you see that here it's the ratio, mobile speed on airflow speed, okay? And so here is 1. So you see that for airflow experiment, this ratio is below 1, which is normal because airflow has to be quicker than the mobile. But what you see is that for techist experiment, we are more close to the motor experiment than airflow experiment. So it's tend to prove that it's not really only an aerodynamic effect, there is another effect in place. And the main case is here because we are at a ratio of 7.8, so we have a mobile running 8 times faster than the airflow around. So, conclusion, in the techist category we see that the airflow is not able to be the only explanation of the running of the mobile. And we also see before that other physics effects have been discarded. So we are in presence of some anomalous effects that needs to further study, and we can say that it could be a macrotech hypothesis. And the second thing is that we present a scientific approach which gives the possibility to scrutinize and to really look a very detailed way the aerodynamic effect around mobile, and so to be able to separate it from potential anomalous effect, and which is very important in an unconfined environment. And for the perspective, we have many things to do. First, we want to reproduce this kind of experiment with good ratio. We want to make some documentation, some other labs will take work and try to do the same. We also work on a 3D approach because, as you see, we make a horizontal slice of the space. We have already done some work with a vertical slice, but we want to combine this and see if we can see if there is some helicoidal effect. It could explain maybe the movement of the mobile. We don't see that now. And also we are very interested and we have make a big work to make artifact experiment as proposed by Alvarado to try to reproduce. My time is left?
No.
1 minute. Okay, perfect. So to reproduce the Barclay experiment, because we try to do that with artifacts like calorimeters or something like that, or obstacle, and we have not have so much success. So I think we have to go further on that and maybe publish something on that. So those other things are confinement and temperature impact, which are very important. So thanks for your attention. A little joke. last experiment, if I have 1 minute. Whoa.
Okay, we have some time for some questions.
First of all, I'd like to congratulate you. It's nice to see some really competent physics in a difficult environment. Are you familiar with the Egli wheel from Hungary, George Egli? You see, is a mobile just like that.
Yeah, we have this.
Yeah, very similar. I don't know if you know Vashi Zoltan. What he did different than what you have done is he took a rubber globe, filled it with 37-degree water, and replicated everything. So have you guys done something like that?
Yeah.
That's it?
That's it. So this is a globe with heated temperature, and they try to do that. And we also, so this is for temperature, so for heat, but we do that also for the obstacle. We work also on artificial hands, wood hands, in order to see, because there is always two effects. There is the heat effect, but there is also the obstacle effect, which deviations, so we create a couple, a torque on the mobile. And so you can combine these two to have some good experiment.
Nice job, you guys.
And we work with many objects, in fact, before your question about Egli wheel, and some heavier objects too. So 250 gram and 2 superimposed. So we have 300 sessions of experience globally, so it's 3,000 video. So it's not all with PIV. It's not so protocol oriented, but we have to, if we want to develop, we have to leave some uncertainty and some flexibility to the people to work and to play. They want to play, they make their video, they send it, and we try to work on it. Thank you.
Yeah.
There seems to be some debate about the hands, how close. I mean, and you mentioned earlier on that people move this object with their hands. I mean, they're not really moving it with their hands.
No.
So why not just not have their hands on the desk? Why do they need
Because some whiny don't work.
You
You need to have the effect. First, you have to need the effect, and I think that it's key. So what we see is that some people, for example, someday they are able to run the mobile without hands, and other days they need to put their hand close, not so close. And about distance, because we very often talk about the distance in psi effect. What we see that when you try to run the mobile, you try at the end that maybe it's 10 centimeters, and if it works fine, you try to move at the end, and at sometimes the mobile stops. But maybe it's at 50 centimeters. And if you have the control of the software to control the airflow, you can see very quickly that it's not a fake, because if people is blowing some air, you see directly on it. Take a question.
Yes, one comment. I'm appreciating your efforts you put into measuring all possible influences, but I think it should be possible to do it without hands, because the hands are only an aid to do it, but it's not done by the hands. And I think people should be able to do this with a distance of 4 meters and without using hands and simply...
I think the people have to do it, yeah.
Eric, it's a matter of how you train your subjects.
Est-ce que tu peux dire de ma part que ce qu'on cherche nous à faire, c'est pas de mettre forcément en avant un effet télékinétique, mais surtout de trouver une anomalie au regard des lois physiques qui s'exercent.
So the point of David is to say that we are more looking at anomalous effect. Being the hand closed or not, it's not the problem finally. The thing is to find an anomalous effect. If you are able to measure and to see that it's not the end, it's doing the job, you have an anomalous effect. So if people are easier, it's really what Brenda Dune and Robert Jones say. You have to leave flexibility to the systems to happen. That's all the people who work on this field see, and we see that all the day. If you want too much to control the systems, very often you inhibit the phenomenon. So some people are working with hand, some people are not working with hand. We make some work also in a confined environment, so with containers, spy wheel, and we are at 1 meter. But you have to see that the spy wheel is very often it's 1/10 of gram compared to our mobile, which is 2.5 gram. So you see also that depending of the weight of the object, you have not the same effect. So I think that you have to use it. I think it's a good approach to see the phenomenon. Yeah, sure.
Okay, I'm going to have to stop the session now, unfortunately. So I'm going to move on.